Hello viewers, so we have this question that says calculate the pH of a formic acid solution that contains 1.45% formic acid by mass. Assume a density of 1.01 grams per ml for the solution. So we are given density of the solution and we are given percentage by mass of formic acid. So let's go ahead and solve it. The first step we're going to take is to find the mass of solution. From the formula that says density, so density is equal to mass over volume, making mass the subject. Our mass is equal to density multiplied by volume. Now we are going to make an assumption to say we have 1 liter of solution and that's the volume we are going to use. So the density is 1.01 and this is in the units of grams per ml. So the units are grams per ml. Since we have the units of mils here, we are going to represent our volume also in mils instead of liters. So 1 liter is equal to 1,000 mils, and that's what we are going to use. When we do mathematics here, we are finding that our mass of solution is equal to 1,010 grams. So this is the mass of solution that we have. Now that we have mass of solution, this will help us establish the mass of formic acid. Using the formula that says percentage by mass, so percentage by mass is equal to mass of a substance, so mass of a specific substance in a compound divided by the mass of the whole compound. So mass of, in this case, we're talking about a solution, so mass of solution multiplied by 100%. So this is a solution that comprises of formic acid, and we are looking for the mass of this substance, which is formic acid in this case. So let's replace. Now what we have here is we have 1.45% on this side, and this side we have mass of formic acid. Now let's specify to say we are talking about formic acid. So formic acid had the formula that I've just written there. So mass of formic acid divided by the mass of solution is 10 grams, and this is going to multiply by 100%. So we're looking for the mass of formic acid. I'm going to multiply this whole situation by 1/100%. So when we do that, you find that this 100 and that 100 will cancel. What you have is, on this side, we're going to have 1.45% divided by 100%. This will be equal to mass of formic acid that we have divided by the mass of solution, which is 10 grams. Well, when you reach this stage, all we have to do is mathematics. So we need to divide 1.45% by 100%. So let's see what we get when we do that. So what we are getting is 0.0145 this side, and this will be equal to, we still have mass of formic acid in this case divided by 10 grams. So when we cross multiply there to get our answer will be, when I multiply 0.0145 by 10, I'm getting my mass to be 14.645 grams. So this is the mass of formic acid that we're looking for. So we have the mass now. Our next step is to find the number of moles for formic acid. So let's quickly do that. The number of moles for formic acid Using our common formula, number of moles is equal to mass divided by the mixture. This is equal to, the mass we have is 14.645 grams divided by the molar mass for formic acid. Molar mass for formic acid is this formula that we have here, HCOOH. So the molar mass for that is basically 46. Using rounded off values, we're getting 46 grams per mole. So when we do our mathematics there, when we divide, what we are getting is 0.32 moles. Rounded off to 2 decimal places, that's what we are basically getting there. Now that we have our number of moles, we can now go ahead and find our concentration. All right. Now, the concentration will be equal to number of moles over volume in liters. So we put it as L down here. And this will be equal to 0.32 moles. And this is going to divide by 1 liter. Remember we said we're using 1 liter as our volume here. So this will still give me the same amount as concentration. So this is what we are going to have as our concentration for formic acid. After doing that, we're going to write the dissociation equation for formic acid. So formic acid, when you put it in water, what we are producing on the other side is we're going to have the hydronium ions, so H3O plus, added to what remains there will be HCOO minus, which is the conjugate base for this acid. After doing that, we're going to write our ice table. So our ice table, where we're talking about I being the initial, C being change, and E being the equilibrium concentration. So the initial concentration we calculated is 0.32, and we have 0 for the hydronium ion, we have 0 for the conjugate base. This is going to reduce by X, it's going to increase by X, and that will also increase by X. It's reducing. This is reducing because we don't have anything on the other side. So the reaction proceeds. This is going to reduce and those two are going to increase. It's going to reduce by an amount that we don't know. So we are representing it by X. Also, it's going to add by the same amount we're representing as X. So then we have 0.32 minus X here, and we're going to have X there. We're going to have our X there. All right. So after doing that, our next step now is writing our Ka expression. So Ka will be equal to the concentration of the hydronium ion multiplied by the concentration of the conjugate base, like that. And this whole thing is going to divide by the acidic concentration, or the acid concentration, like that. Replacing with what we have now. Formic acid has got a Ka value of 1.8 times 10 to minus 4. So we're going to replace with that, and this is equal to, on the other side, the concentration for the hydronium and the conjugate base on top are both X, so we can just say that is X squared. And then down here we have 0.32 minus X. So let me clean the other part here so that we can use it. All right, so what we have there is we have 1.8 times 10 to the power of minus 4. This is equal to X squared. And down here, at this point now, we're going to ignore the X down. So this x that we have here, we're going to ignore it. Using the 5% rule, we are saying the reduction in the initial concentration will be very small, that it will be less than 5%. So we can ignore this x here because the change will be very small. All right. So when you read that point, it means now all we are doing is we are finding the value of x. So we are going to say we cross multiply, x squared will be equal to 1.8 times 10 to the power of minus 4 multiplied by 0.32 on that side. Then our x will just be equal to the square root of that everything we have here, which is 1.8 times 10 to minus 4, like that, multiplied by 0.32, like that. And the value of x when we do our mathematics here would be 7.59 times 10 to the power of minus 3 molar concentration. So this is our molar concentration, 7.59 times 10 to minus 3 molar concentration. So what we have found here is basically the value of x, which also happens to be the concentration of the hydronium ion. So that value of x is the concentration of the hydronium ion. Since we have the concentration of the hydronium ion now, our pH is just equal to negative log of the hydronium ion concentration, like that. And this will be equal to negative log of the concentration we have is 7.59 times 10 to the power of minus 3. So when we punch our calculators there, negative log of 7.59 times 10 to minus 3 is giving me 2.12. So this is the value of our pH.